Hey everyone, welcome to this explainer. If you've ever tried looking at a full machine learning glossary containing all the definitions, it's a lot. It can easily feel like you're trying to decipher an alien language. You've got all these incredibly dense, highly technical terms floating around, and it is so easy to just get lost in the weeds. But today, we're doing something different. We are going to take that massive glossary of dense machine learning jargon and decode it into a highly logical, totally accessible crash course. We're going to break down that barrier to entry and make this fascinating technology crystal clear. Let's get right into it. So instead of just reading a glossary alphabetically from A to Z, which would be pretty boring, we're going to follow the actual life cycle of how a model is built. The basic building blocks, the training process, measuring success, and finally, generative AI.
Starting off with part 1, the basic building blocks. Okay, so before a machine can learn literally anything, it needs raw materials. It's kind of like a chef needing ingredients before cooking a meal, right? An AI system needs specific types of data structured in a very particular way. In our full glossary, the first absolutely crucial term is a feature. In the machine learning world, a feature is simply an input variable to a model. Think of it as the basic data point, the clue that the model looks at to learn patterns. If you're trying to predict the weather, your features might be things like temperature, humidity, and wind speed. They are the raw data the machine uses to solve the mystery.
But what exactly is the mystery we want the machine to solve? That brings us to our next essential term, the label. In what we call supervised learning, the label is simply the answer. It's the ultimate destination or the final result portion of a specific example. You feed the machine all those features we just talked about, and you want it to accurately guess the label. To really visualize this, let's look at some housing data. This brilliantly illustrates how these concepts play together. We've got our continuous features right here, the number of bedrooms, the number of bathrooms, and the house's age. Those are our input variables. And what do they map directly to? That final column, the house price. The price is our label. The whole goal is to get the model to eventually look at a brand new house's features and correctly predict that final price tag. All right, so we have our data, our features, and our labels. But what is actually doing the heavy lifting to process all this information? Well, very often, it's a neural network. This is a model that takes its inspiration directly from the biological brain. It is the architectural engine that will eventually process those features to predict the labels. But to really grasp how it does that, we kind of have to peel it back and look inside. I like to think of a neural network like a Matryoshka doll, those Russian nesting dolls. When you open the network up, the first thing you find is a layer. A layer is just a set of neurons within the network. And there are three main types you need to know. The input layer, which receives the raw features, the hidden layers, which do all the complex behind-the-scenes math to find nonlinear relationships, and the output layer, which spits out the final prediction. Now, let's open that Matryoshka doll one step further. Right inside that hidden layer is the node, which is also called a neuron. This is the individual little mathematical worker bee inside the network. What a node does is it takes a weighted sum of all the inputs it receives, manipulates them mathematically, and passes the result on to the next layer. And we are talking millions of these tiny calculations happening simultaneously. That's where the massive power of the model actually comes from. Moving on to part 2, the training process. So we have our mechanical brain, our neural network, and we have our data. Now we head to the training ground. This is where the magic happens. Our next key glossary term here is, unsurprisingly, training. Training is the meticulous process of figuring out the ideal parameters, specifically the weights and biases, that make up a model. Essentially, the machine looks at an example, makes a guess, checks the actual label, and then slightly tweaks its internal mathematical dials so its very next guess is just a tiny bit better. And it does this millions or even billions of times.
But here's the thing, it doesn't look at all the data at once. That would be completely exhausting computationally. Instead, it processes a batch, which is the set of examples used in one single training iteration. But honestly, more often than not, we use a mini batch. That is a small, randomly selected subset, usually between 10 and 1,000 examples. Slicing the massive data down into these digestible chunks allows the model to process information and learn way more efficiently.
Now you might be wondering, during all this training, how does the model actually know if it's doing a good job? Well, it measures its loss. Loss is the mathematical calculation of how far off a model's prediction is from the actual label. If the loss is high, the model is failing. Loss is literally the ultimate enemy during training. It's the mathematical distance between a bad guess and the right answer. The absolute goal of every machine learning model is to minimize its loss.
And we can actually visualize this battle against error using a loss curve. This is a plot showing the loss value over the number of training iterations. When you're training a model, what you really want to see is this curve diving downward over time, sliding right down the graph. Eventually, that downward curve is going to flatten out, and when the loss stops decreasing and levels off, it means the model has learned pretty much all it can from the data. That beautiful flat state, that's what we call convergence.
Which brings us to part 3, measuring success. Okay, so our model has converged. Training is officially complete. But how do we actually know if the model is genuinely smart or if it's just faking it? The very first, most intuitive metric everyone goes to is accuracy. Accuracy is simply the number of correct predictions divided by the total number of predictions. If it guessed right 80 times out of 100, boom, 80% accuracy. Sounds flawless, right? Well, actually, scratch that. I'm going to warn you right now. In the world of machine learning, relying solely on accuracy can sometimes be a very dangerous illusion.
And the reason why brings us to another major term in our glossary, the class imbalance dataset. See, real-world data is almost never perfectly symmetrical. A class imbalance dataset happens when the total number of labels in one category vastly outnumbers the other. And when you're dealing with highly imbalanced data, our old friend accuracy suddenly becomes completely useless.
Let me show you exactly why this matters. Imagine we build an AI to predict if it's going to snow in a hot subtropical city. It snows maybe 25 days in an entire century. Our model decides to cheat. It just blindly guesses no snow every single day. Look at these numbers. It gets 36,499 days right. Those are our true negatives. It only misses the 25 days it actually snowed, the false negatives. If you calculate the accuracy on that, this model is 99.93% accurate, but it is totally useless. It didn't predict a single snowy day. It has zero actual predictive power. And that is exactly why we have to use much more advanced metrics than just basic accuracy when testing real-world models. Finally, part 4, generative AI. Now that we've nailed down how classic models learn and how we test them, let's step into an exciting new frontier and contrast the two. Everything we've covered so far, predicting house prices, predicting snow, that is predictive ML, standard classic machine learning. It looks at features and predicts a label. Generative AI is a whole different ballgame. It doesn't just categorize data, it creates entirely new content based on complex probabilities. We are moving from the old world of simply labeling data to a new world of dynamically generating brand new text, images, or even code. The absolute star of this generative revolution is the language model. We interact with these literally every day now, but let's demystify the magic behind them. A language model is fundamentally just estimating the probability of a token, or a sequence of tokens occurring. It isn't thinking in the human sense. It's just looking at the words you typed and calculating the highest mathematical probability of what the very next word should be, word by word, to create a coherent sentence. But let's see how this builds into something even more incredible, the agent. An agent is software that doesn't just passively talk to you. It can actually reason about your inputs to plan and execute actions on your behalf. We are crossing the line from a digital chatbot into an autonomous digital worker that can actively use tools and interact with other software. It's a real game changer. So how does an agent pull this off? It utilizes the agentic loop. First, it observes its environment and the tools it has available. Second, it reasons about the specific problem it needs to solve. Third, it acts. Maybe it sends an email or queries a database for you. And finally, it receives feedback on that action. It dynamically self-corrects and repeats this loop continuously until a specific termination condition is met, meaning it keeps going until the job is done perfectly.
And that brings us to the end of our life cycle, leaving us with a really profound question to ponder. What happens when models act entirely on their own? We started this explainer looking at basic features and labels, simple rows on a spreadsheet. And in just a few logical steps, ticking off our full glossary containing all the definitions, we've arrived at fully autonomous agentic workflows capable of observing, reasoning, and acting without our constant supervision. The machine learning lifecycle is evolving at breakneck speed, and understanding this comprehensive foundation of terms is for sure the absolute best way to ensure you're ready for whatever comes next. Thanks so much for joining me on this explainer, and keep learning.